Hi, welcome back to es346 Basic Thermodynamics. This is module 6.4 on perpetual motion machines and reversibility. Sections in the textbook are 6.5 and 6.6. Here are the two learning outcomes from this module. At the end, you'll be able to define the two types of perpetual motion machine, and you will understand the concept of thermodynamic reversibility. So first I want to come up with a definition of a perpetual motion machine, and I took this one here from Wikipedia. I think it's pretty good. It says a perpetual motion machine is a hypothetical machine that can do work indefinitely without an energy source. There's two types of perpetual motion machines. The first is called a type 1 perpetual motion machine, and this is from the textbook, and it gives an example of one. So what this has is a boiler. It's kind of like a traditional power plant. And it's going to go ahead and supply some steam. We're going to run through this turbine. This turbine's going to go ahead and generate some work. And then we're going to go ahead and go through a condenser, and it's going to dump some energy Q out. And then we're going to, again, run through the pump. Now what's different, though, is instead of accepting a QH from the outside, like from burning coal, what we're going to do is we're going to take some of the energy that it generates from this generator here and go ahead and run it through the boiler. So there's no QH in here at all. Well, if you do an energy balance across this, first law energy balance, we realize that what we have is it's generating work and it's dumping Q out, but there's no arrows going into it. And we know that this cannot operate on a cycle. And from thermodynamics, the first law of thermodynamics, we realize this cannot exist. Therefore, it's called a type 1 because it's violating the first law of thermodynamics. Here's an example of a type 2 perpetual motion machine. And again, what we have is kind of like a traditional power cycle. Here we are actually accepting heat from the outside, QH, into this boiler, running it through a turbine. It's generating some work. But what's different is we've gotten rid of the condenser. We're just going to go ahead and pump that fluid right back through the pump. And so if I look at my device now, I've got QH coming in, and it's generating work. And so from the first law, all it says simply is QH is equal to W. So it doesn't violate necessarily the first law of thermodynamics. But what we saw is it does violate the second law of thermodynamics. We looked at the statements of the second law before, which said you can't accept energy from a single source and go ahead and generate work. And so this violates the second law of thermodynamics and is called a type 2 perpetual motion machine. Well, what's interesting about perpetual motion machines is that the United States Patent and Trademark Office will not patent perpetual motion machines. In fact, let's go ahead and go to their website. And here's their website, and if I go ahead and just scroll down a little bit, you'll realize right about here, inventions which you cannot do, and one of them is perpetual motion machines. They will not accept a patent for a perpetual motion machine. So if you violate the first or second laws of thermodynamics in your patent, in your patent application, they will not grant you a patent. Well, here's a kind of a classic example of a perpetual motion machine that was proposed by George Hayes in 1861. It's a pretty complicated device. It's got a whole series of gears in here. But the basics behind it was there's this lever arm here that a person would go ahead and turn. So they would go ahead and put some work into it. And because this gear here was free to move, it would go ahead and want to kind of fall down, which would cause this gear to turn, and through a whole lot of complicated mechanisms, there would be a power generation coming out of this bottom here. It would be work out, and it would be greater than the work that went in. This would be the work that went in. And he wanted to go ahead and patent this. Well, this is clearly a perpetual motion machine. We're getting out more than we're putting in. And so you would say, well, of course that couldn't have gotten the patent. Well, it turns out that the British did patent this. They patented it in 1861. It's patent 1112. So there have been devices that are perpetual motion machines that have been granted patents in the past. And I want to talk about reversibility and thermodynamic reversibility. And here I have a diagram from the textbook that gives an idea. And one of the things about reversibility is that in order for something to be thermodynamically reversible, we tend to find that they cannot occur too quickly. And so to kind of get that idea, let's look at this. I've got a section of water here in a tank, and it's going to go ahead and expand. And so it's going to go ahead and expand, push this wall back. And so we know that the work is the integral of a force through a distance. And so we're getting some force over here. In fact, we could go ahead and say that that's going to be P dV, which we've derived before. And then as we go ahead and store some work, maybe it's going to go ahead and store it in a spring. And then this spring, once it's compressed, we go ahead and go back again and push this water back. Now the amount of work each time we realize is going to be the pressure across here, and the pressure kind of changes with depth. So we go ahead and integrate that in order to determine the work that's getting stored in this spring. If this occurs slowly enough, I'm just doing a W to W transformation. Effectively, I'm turning potential energy into spring work in this example. And I can go ahead and do that indefinitely with 100% efficiency. Now, however, if I was to do this very fast, so now I'm going to go ahead and move the wall so quickly that the water cannot keep up with it, what I realize is I'm getting less work out each time, because this wave over here, this is going to be lower. You realize it's a little bit smaller than that side. The amount of work that I'm going to get out is going to be less than before. And the other thing, if I compress it back in very quickly, the amount of work that goes in is going to be more. So the work that is going to go in is going to be much greater than the work that goes out. And so although I'm doing a work-work transformation, they're not going to be equal. So this thing down here is an irreversible energy transformation because it's occurring very quickly. Another type of irreversibility is due to heat transfer. And so we can kind of think about why that is imagine I have a mixture here. It's at 25 degrees Celsius. I have an initial quality of 0.5. It's 150 kPa, and it's at a constant pressure. Now, if I go ahead and add some energy to here, it's going to stay at 25 degrees Celsius. I could go ahead and it will expand. It will do some work. There will be an increase in its internal energy that will be balanced by Q. In fact, I could write that energy balance here and say Q is going to be equal to delta U plus W. And there's nothing to say that if I was to go ahead and compress this back, I could go ahead and get my heat back out. And that would be reversible inside this system. However, though, if this is at 25, in order to put the energy in, this would have to come from TH, which is greater than 25 degrees Celsius. However, to get the energy out, this would have to be TL, which is going to be less than 25 degrees Celsius. And so we see that this is actually an irreversible. The energy transfer by heat is an irreversible process. So anytime you have heat transfer through a finite temperature difference, that will be irreversible. Another term you'll often hear is whether something is internally reversible or externally reversible. And so kind of similar to the example that we just had on the previous page, you could be adding heat to a mixture. And that energy, that Q that's coming in, call it QH, could be going into an increased internal energy, also going into some work. Now inside, the contents in here, that is entirely reversible. There's nothing in here going on that's through a finite temperature difference. The only things that are going on is outside here where we said that this pH, has to be greater, in this case, it would be greater than 20 degrees Celsius. So it's going to be externally irreversible. The processes that are going on inside are internally reversible.